Let's see. Are we live? I believe we are. Let me go ahead and grab the stream over here. Grab that stream. Okay, got it. And now we'll say live again. Oops. All right, didn't mean to do that. Again. Questions. There we go. Okay, so the question. Course schedule 2. Total of n courses you have to take labeled from 0 to n-1. Some courses may have prerequisites. For example, if prerequisites of I is equal to a sub I, b sub I, this means you must take the course b sub I before the course a sub I. Given the total number of courses, num courses, and a list of the prerequisite pairs, return the ordering of courses you should take to finish all courses. Excuse me. If there are many valid answers, return any of them. If it is possible to finish all courses, return an empty array. Total n courses, 0 to n-1, prerequisites means you must take course b sub I before the course a sub I. Given the total number of courses, num courses, and a list of the prerequisite pairs, return the ordering of courses you should take to finish all courses. Given the total number of courses and a list of the prerequisite pairs, return the ordering of courses you should take to finish all courses. Ah, that's interesting. So this is a graph question. This is actually a pretty interesting question. This is called an Eulerian tour. Take a quick look. So graph theory, Eulerian trail is a trail in a finite graph that visits every edge exactly once. No. This is a Hamiltonian, not a trail or path. It's a little bit different. Hamiltonian path. So this is a very interesting question. Very interesting question. This is the Hamiltonian path, and path of an undirected graph that visits each vertex exactly once. Yeah. So what's interesting about this is this is an interesting question. So you actually don't need a Hamiltonian path. A Hamiltonian path would be sufficient for this question. However, a Hamiltonian path is NP hard. NP complete, excuse me. It's NP complete, which means it's very difficult to solve in general. This question, however, is just a simple graph search, because you can use any ordering of the courses that is sufficient. So you can do a simple breadth first search. You just need to make sure that you visit every node. So we can do this like really quickly, I think. But one thing you need to do though is actually build the graph in order to perform the breadth first search. So we'll do that. Yeah. The pre-processing step, I mean, it doesn't need to be that complicated. It could literally just be a this could actually be really simple. Prerequisite pairs. Yeah, I think this is fine. Assuming you don't have duplicates, then we can actually do what you won't. So you can just do a simple hash map. So you can just do a pre-processing step. Pre-processing to build adjacency matrix or adjacency array, we'll call it. We just do a simple for. Now this is kind of neat. Can you do this? A XY in prerequisites. Well, then we say unordered map of int to int, and we're gonna say adjacency, adjacency, adjacency. We'll just call it adjacency array, or just adjacency array. And we'll say adjacency array of x dot pushback y. That should be standard vector of int, right? Yeah, this will actually create the vector, which is pretty cool. Once you call this, and then the dot pushback should be, yeah. Okay, and now what you're gonna do is BFS. So auto BFS equals. Actually, no, you don't even need to. No, you're fine. You just do a standard queue of. I guess it'd be integers. And call it Q. So while Q is empty, well, the Q isn't empty. So what do they want? Many valid answers, return any of them. It's impossible to finish all courses, return an empty array. Okay. Oh, that's interesting. We're going to say return ret.size equals num courses. If it's true, then you're going to return ret, else you return an empty vector, an empty array. And these also should have things in there. I don't think I'm going to modify this at all. So this is const, and this is also okay. And then typically, if it starts to run off the screen like that, I like to just throw that in there. So right, create this adjacency array. You create this queue. Initialize the queue at. Oh, that's a good question. We don't know where we should start the queue at to do the breadth first search. Oh, that's pretty awkward, huh? You can run the breadth first search on every node. Oh, that's a very good question. Oh, wait a second. Yeah, this is undirected. Oh, I didn't think about that. This actually would create a DAG. Oh no, oh gosh. This is a tree. This is a directed acyclic graph, or otherwise known as a tree. Basically, you want, actually in this case, this is a little bit more tricky than what I thought, because if this was a undirected graph, it's really easy. You can pick any node, shouldn't matter. However, because it's directed, some nodes won't be able to reach other nodes. Ooh. That's very awkward. I didn't think about that. Ooh, shoot. If you knew of a node that could reach every other node, then you can make that the root, and then obviously you can just read off the children. Oh no. You do a breadth first search from that node, reading off the children one by one, but actually you need to find that child. Now, here's the thing. Oh, wait a second. I guess you need to find nodes that don't have any incoming edges. Actually, yeah, so I guess what you need to do is, in order to find the root, you need to find nodes that don't have any incoming edges, because the root necessarily doesn't have an incoming edge. However, could there be multiple roots? No, there can't be more than one. If there's more than one root, that means that they can't ever reach each other, because they don't have any incoming nodes. So if there's more than one root, you could just return false immediately. Okay, so while we search for these prerequisites, we'll say we can actually determine, how do we find the one that doesn't have an incoming doesn't have an incoming. Well, we could do something like this. I mean, this is fine. This isn't like the most efficient way, but we can do this. So incoming, or is root, we'll say, and then we'll say that's false, or no, true, and then we'll say num courses is the size, and then we say is root of y equals false, right? So if it's on the right, if it's on the incoming edge side, right, something's going to y then, and it's labeled 0. So fortunately, we have a mapping of these things. They're labeled as integers, 0 to n minus 1, so it works out nicely. And that's kind of neat. So then we can say get root, which is the only node which has no incoming edges. If there are more than one, then we return false. Cannot reach each other. So for auto x in his root, or even, you want to do it this way, I equals 0, less than is, or just n, of courses. If is root, then we'll say root. First we'll start off at -1, so root equals root equals, so the is root, say if, if root equals -1, then we'll set root to I, else return false, or return an empty array. Yeah, return an empty array. There we go. Now we can continue what we're doing. So now we can push the root, which is yeah, the root of the tree, and now we can do a breadth first search. So each child is going to be the adjacency array. So we're going to say for auto x in the adjacency array of q, or I don't know, we'll do int next, there was the next v, and the next value is q dot front, and then we q pop, and then we say in the adjacency array, and we also push v into the return array. For each value in the adjacency array of v, we push those values into the queue. So queue.push x. And that should do it. Oh, cannot decompose members of an accessible base class. Really? That's kind of annoying. Pair, really? I thought you could. No, okay. That's kind of disappointing. Can I use the destructuring syntax here? And vector decomposes into one elements, but two names were provided. Is that true? Can we not destructure vectors? I guess we can't. That's kind of annoying. Vocoder. Yeah, I'm looking for more like the Stack Overflow. Oh, destructor, no, destructor, not destructor. Destructor. It's different from destructor. Why? You can do tuples, but you can't do, and you can do pairs, but you can't do vectors. It's kind of frustrating. I don't know. I don't know what the deal is exactly, but that's okay. Let's just say int is x is pair 0, and y is pair 1, I guess. I guess we'll do it this way then. Bool is root. If is root of I. Yeah. Does not provide a call operator. I think I need this also. Oh gosh. Yeah, well I do want that, but also it's thank you. And cannot be used on the right hand side of operator. Oh. No kidding. Really? Okay. That's kind of weird, but I guess it is what it is. Sure. That's kind of unusual. Wrong answer. Input 2, 1, 0. One output 1, 0. Expected 0, 1. Oh, is this? This means you must take the course B sub I before A sub I. Ah, B sub I is the other way. Ah, okay. Gotta reverse these things. Y and X. Okay, fine. Did I get it right? Okay, there we go. All right, it's yeah. So part of the issue is, right? I interpret it as A before B, but it's actually B before A. So B would point to A. So this is kind of interesting. Do they give us? Okay, what are some other examples? Let's see a few of their examples. Just at least pass their examples. See how that goes. Pretty interesting question. Kind of a useful question when you're in university. Really useful question in university. Definitely something I've done it by hand a few times. I recall doing that. Wrong answer. Oof. No kidding. Okay. Oh no. This last one was no dice. What happened? The middle one. All pairs are distinct. Yeah, that's what I was gonna say. I think they need to be distinct for this to work nice, work well, or to make sense. So 1 0 2 0 3 1 3 2 output 0 2 1 3. There are a total of 4 courses to take. Take course 3. Should have finished both courses 1 and 2. No. Oh. I was wrong about this. The root being. Oh gosh. Oh no. Wait a second. Wait. If it's impossible to finish all courses, return an empty array. It's not impossible to finish all courses because, oh, that's if there's a cycle. Ooh. Oh gosh. Okay. I see the problem. No, it doesn't even matter if there's, yeah, oh, it does. No, it matters because, yeah. Okay. This question is pretty funny. Oh my gosh. It's too funny. Okay, I screwed it up, man. I screwed it up. It's good that we did it here because I messed up. No. The condition that there's no, it's not no possible option is if you have a cycle, you have circular dependencies. That's when you have a problem. And then what you can do is just do a breadth first search on each of the roots, each of the courses. You make an array of the courses that don't have any, an array of the, so each root you throw into a directed acyclic. Actually, really what you should do is just put every root into a, actually, no, wait, this gets kind of confusing now. No, wait a minute, because you can have crisscrossing and stuff. You can have all kinds of, you want to do every root first. Definitely. Oh no, man. No, it's not as easy as I thought. Oh no, I programmed it wrong. Oh. So first things first, you want to make sure you don't have any cycles. Second thing, probably, I guess you, yeah, you could do the breadth first search from every root node is kind of awkward. The thing that's weird is like, you know what you might want, it would be the easiest way to do this. Because all right, hold on. Let me, I think the way to do this is to do a level order traversal. That's probably the easiest way, where each level is the, actually starts with all the root nodes, right? All the nodes that don't have any pointers coming in. So do all those first. And then for each of those, right, obviously there are nodes that are, that those are prerequisites to, right? So all the nodes that those are prerequisites to, then you want to do all those nodes where you have all the prerequisites. right? So basically what you'd want to do is do a level order traversal where you do all the nodes that you have the prerequisites for at each step. And then if there's any left over, and then if there's any left over after that, then you would return false, or you return the empty array. This is so funny, man. This is crazy. And then what would be left over would be the ones that have circular dependencies. But now the question is, how do you easily determine if you have all the dependencies for a node? That's kind of a, like, so one way to check it is you just literally have a set of all the things that you've already like taken, and then the node you say find me the set of all the things you've already taken, and then find me the given a node and all of the prereqs that are required. Do I have all of them, right? So you just do a set to set check on all of the neighbors, I guess it would be, all the neighboring nodes. Now the question is, you could do it that way. You could do it that way, set to set check on every neighboring node, where the neighboring node is like something that you know you're a prerequisite for. Also throw all those into a set. So you find all the neighbors and throw those into a set, and then you check for each of those neighbors which of them has all the prereqs, right? So you can do this. However, it's kind of expensive, isn't it? It's kind of awkward. It's also fortunate that they only put 2,000 nodes here. That makes things a little bit easier, I think, if you do, what's 2,000 cubed? Although, I don't know, I think it still has to be somewhat quadratic time if you cube this. So actually, this is a very good question. 1,000 million billion. I think I will time out if I don't do this properly, if I don't do this like more efficiently. Oh man, gosh, I got beat up. I got beat by this question, somewhat beat. No kidding. Okay. No, man. It's like a classic question too. Oh, shucks. There's a lot of ways to do this, but this is like not the most efficient way that I'm about to do it. Do your level order, right? Do that one, and then create a set of neighbors, right? So you don't insert into the set until if you've already added that. So you build this set of neighbors as you go, and then for each of those neighbors, so you do need both directions. You need to know the nodes coming in and the nodes coming out. Now the question is, I want to say something like oh man, it's super awkward. It's super awkward. It's very awkward, isn't it? Yeah, it is. Yeah, because There's got to be a better way to do this. It's more efficient. It's basically once a node has all of its prerequisites. Oh no, man, no! There's got to be a better way to do this. The thing is, there's so many answers. There's so many ways to do it that like there's got to be a way that's like efficient. It's like really simple. Oh gosh, man. Oh, it's too funny. It's too funny. This is like, gosh. No, if I got this in an interview, I probably would fail the interview. No, man. So I want to say, what you can do is the nodes. I want to say like keep track of all the nodes that have a certain prerequisite, and then remove the prerequisite from all those nodes each once you add the prerequisite. Probably better would be to increment each of those nodes or decrement each of those. So each node has like a certain number of incoming edges, and then once you when you process a prerequisite, when you process a class, all of the outgoing edges you decrement that node, right? And then when you're considering neighbors, then I guess what you would do at each step is just look through all the nodes again. No. When you decrement the edge, check if it's a 0. That's what you do, and then you add that to the neighbor set. That's going to be the next level that you. Aha! I got it. I think we got it. All right, let's do it this way. So, still do the same old adjacency array. Still do isRoot. So we don't. So what we're going to do now is actually it's going to be incoming edges. There we go. Incoming edges, and it's going to be 0, right, for everything. Yeah, I like that. There we go. And now what we're going to do is say incoming edges of, so y is a prerequisite for x, so x has to be done before y, right? That's how it's read. Y has to be done before x, right? So y is a prerequisite to x. So if y is a prerequisite to x, that means that x has an incoming edge, which is y, right? All right, so initialize with all of the possible roots, or all of the roots. So there actually could be cycles. No, there can't be cycles. Yeah, there can't be cycles, which is interesting. Is that right? There can be crossover though between these forests, right? Possible, yeah. So this is a forest of trees, sort of intermingling trees. So this is not a directed acyclic graph because no, it is. Initial courses. The queue of the initial courses. Yeah, this is a very interesting question. It's a directed acyclic graph could have sort of multiple roots. It's not a tree. It's not a tree. It's slightly different from a tree because you could have crossover. That's why. Trees don't have crossover. That's why they're a directed tree. It's not a directed tree. It's a little different. Slightly. Here's a case where it's a directed acyclic graph and it's not a tree. And there are some cases where if you use a tree, like that was what I just did. Using a tree would have a single root. This could have actually sort of multiple roots. Super interesting question. I like this a lot. This is great. So I say if incoming edges is 0, then we can say take our queue, say ret queue, and we're going to say queue.push q.push. Actually, what you want to do is we'll just push all these. Yeah, that's fine. So push q.push I. Yeah, interesting. Okay. And then while q is not empty, and you do a level order traversal. So what you're going to do is while q isn't empty, you're going to have standard q next level. You're going to do the following. Okay. While the queue isn't empty, you have this next level queue. You say v is queue front, queue pop. You're going to push all these we know we already have all the prereqs. So we push all the values into return, and then we say for each value in the adjacency array, right? So these are all each child. You're going to incoming edges of x, you're going to decrement, and then you're going to say if the incoming edges less than or equal to 0, right? Then it actually has to be 0. It'll always, I don't think you'll ever go below 0, because once you've added the prerequisite, each prerequisite's unique. So yeah, so once it's 0, then we can say q dot, so it's going to be next level dot push x. And then we say q equals next level after you empty the queue. Right, now you're just going to use a copy constructor or move assignment. Move assignment, it's going to use to move the next level into queue automatically. And then we have this down here. So if return size is the number of courses, return red, otherwise empty vector. Something like this. This is pretty interesting question. Pretty interesting approach here. What's wrong? No visible constructor. Oh, because it's got to have. Yeah, these are ints. Everything's an int that we're using. Incoming edges of x is 0. Runtime error. Nice. Non-zero offset forward to null pointer. Whoops. What did I do? No. How did I do that? How did I manage that? Did I just want to see. What did we get here? Oh, we didn't reach here. Okay. Is this? Huh. Where is this happening? Once, and then immediately incoming edges. Doesn't this work this way, Mike? Hold on. I can take a look at the constructor. Pretty sure fairly certain the constructor has an integer count and the value. Oh, whoops. That's kind of funky. Okay. That's a little confusing. That's a little confusing. Whoops. Oh, it's correct. All right. Yeah, okay. I was gonna say, I'm like, oh, I think doesn't the number come first? So I put the number there, but actually, there's two numbers here for this because it's a vector of integers. So the size of the vector is an integer, and then the integers themselves are integers. The initialization value is an integer. So normally I'm like, wait, doesn't the integer come first? It's like, yes, it does, but yeah, it's the wrong integer. All right, I think we got it. Yeah, that's good. Interesting question, man. Interesting question. Nifty question. I kind of want to throw in a bunch of other test cases to see. Okay. I don't know. Can we do 10 different courses? And I want like a graph. This is going to be kind of tricky to put together the test cases, but we want like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know. Let's make the graph look kind of crazy. Let's have like a few different prerequisites that are sort of the root nodes, and then we'll have like, we need a whole bunch of these for this guy. Now what's interesting is maybe we could have, this is a prerequisite for this guy here, and it's a DAG, so there's no cycles, right? If there's a cycle, then it's not a DAG. But we can have crossing here where this makes it not a tree. This kind of like, there's sort of multiple roots, makes it not a tree. So we'll have 10 courses, and we'll do, this is kind of a lot of different, what do you call that? I'm gonna number each of these pairs. Have at least 10 pairs. What I'm gonna do is just transcribe this. Is just make sure every pair has a number, and then make sure I have each number pair is present in my list. One that has a number 2, 3, 4. Oh, 1, 2, 3, 4, 5, 6, 7. It's got one. 8, 9, 10, 11, 12. Hopefully I didn't miss one somewhere. Yeah, these are kind of like wonky examples. They're really just, it's kind of a lot to put together the examples. So 1, 2. Oh, actually I gotta subtract 1 from every number too, because it's gotta be, well, you know what we could do? We could throw 11 in there and then just make 0 have let's make 0 a prerequisite for 1. Could actually make 0 not have any prerequisites, not a prerequisite for anything. So there you go, that'll be interesting. So 0 is going to be in there, so it's actually 11. So 1, 2, and then 1, 3 it looks like. And 1, 2, or no, excuse me, 1, 6, 1, 5. 1, 5. Where's 2 going? 2 is 2, 8. I don't know, wait, we said 1, 2, 3, 4s, yeah. 5 is 3, 2. 6 is 3, 6. 7 is 3, 7. 8 is 5, 9. 9 is 6, 9. 10 is 7, 9. 11 is 410. And 12 is 48. Okay, what does that look like? Oh, works. All right. Sure. 10, 9, 7, 6, 5, 4, 3, 2, 1, 0. Expected output. Really? Wait, no. What? Wait a second. What? Oh no! Oh, I did it wrong. Oh no. I have to reverse all these. Alright, well. Okay. Oh no. 2, 1, 6, 1, 5, 1, 8, 2, 2, 3. Yeah, because the way it's described, the problem is described. Okay. And 10, 4. It took so much time to put together this test case. I think I still get it correct. Alright, so I said 0, 1, 3. Where's my, I said go 0, 1, 3 first. Because it doesn't have, oh, 4 should be in there too. 0, 1, 3, 4, I think. Right, and then do 5, 2, 6, 7. 5, 2, 6, 7, because the prereqs are, we have the prereqs for all of them. And then I guess you also have 8 at that point. You don't have 8 yet. You don't have 2 yet, so you don't have 8 yet. 5, 2, 6, 7, and then 3, 8, 9, I think is next. And 3, 8, 9, 10. Oh no, 3, 5, 2, 6, 7, and then 8 and 9. You don't have. You do. Do you have 4? You do have 4. Yeah, yeah. You actually can get 10 with. Once you have 2, you do 8. Yeah, 8, 9, and 10. I think. At the end, or 10, 9, 8. Yeah. But they said do 4 and then 10, and then 3, and then 7, and then 1, and then 5, and then 6. I have 3, and then 9, and do they have 7 or yeah? And then 2, and then 8, and then 0. I don't know how they did theirs. It's kind of funky. I guess you could do depth first search probably, using a similar thing where you basically assign to every node an number of incoming edges, and then do a depth first search sort of at each root. That's probably what they did. So 4 to 10, right, and then obviously 8 doesn't. Or no. I think it's still a breadth first search. Yeah, well, it's a depth first search on every child. No, it's a depth first search on every child. Yeah, so 4 and then 10, and then went to 3, and 3 had didn't have 2, but you had 6 and you had 7. So then it did 7, and then 9 had and that was it. And then I think, did it go to 6? No, 6 had a 1, right? So it couldn't go to 6, couldn't go to 7. It could only go to 7, couldn't go to 6 or 2. And then 1 doesn't have any, has 0. So then 1 goes to, can't do 2. Oh no, you can do 2 now because you have 3. What did it pick 2? No, it went to 5 first. So 5, and then you don't have 6 yet, do we? We don't, but we can get 6 now. So 1 goes to 6 next. We have 3, And then 6, then we still can't go to 9. Oh, we have 7, right? So I think 6 can go to 9. Yeah, because it's 7. And then 2, 8, and 0. Right? And then 1 goes to 2. Which can then go to 8 now. And then we're done, actually. And then 0 is the last root left. That's pretty fun. That's pretty interesting. So this you could do the same algorithm, but a depth first search on each node that doesn't have an incoming edge. That's fun. Interesting approach that they wrote. I like. Yeah, I'm pretty sure that's what they did. The depth first search on each of the. Yeah. All right. Let's see how we do. Hey, we got it. Sweet. Okay. That was also like a full hour. Gosh. Man, I got beat up by this question. I got beat up. That's a good one though. This is a fun one. This is a good question. So let me get going. I will now. Oh, the one problem though, by the way, with the depth first search is you have to be very careful about. Oh no, you wouldn't have a problem. I was gonna say, yeah, you gotta be careful about the cycles, but actually it wouldn't matter because if you could use the incoming edges as I did here, you have the same deal. So let me get going. I'll talk to you soon. I think I'm going to go ahead and go get myself some food. Probably take an hour to eat, and then maybe come back and do one or two more questions like this. So, all right, take care. That was fun. That was interesting.